Today we're going to be looking at successive substitution, which really just means we're going to be using the Gauss-Seidel method, but for nonlinear systems. Okay? And before we actually start that process, I'd like us to actually get an estimate of what the solution is. So let's maybe solve the two equations above for x2. See what we get here. So if we were to solve that first one for x2, that would look like 10 minus x of 1 squared. And then I would divide that by x of 1. Right, and the second equation, this is actually a quadratic equation. If we were to subtract the 57 on both sides, we could actually use the quadratic formula. And so there we'd have x sub 2 is equal to, and then we'd have minus b, and so b for us would be 3. Ooh. If we were to rearrange this a little bit, this would be the a term here. This is the b term, which is actually just 1, the number 1 in front of it. Okay. And then this is c over here, but we'd have to subtract that over. Okay. So actually we'll have minus 1 plus the square root of b squared, so it's 1 squared minus 4 times a, and a is that 3 times x sub 1. Okay. So we have 1 minus 4, then we have a, and then the last thing we need is c, so times negative 57. Okay, and then this is all over 2 times a, okay, which is 3 times x sub 1. All right, so now that that's done, I do want to point out that the quadratic formula actually comes with a plus or minus here. Okay. And so we'll actually get a solution based off of the positive square root and the negative square root here. But we're just going to focus in on just finding one of these solutions for now. Okay, so let's go ahead and plot it and see the one solution. So in order to do that, let's go ahead and pick some values for x1. Let's say we're going to go from 1 to 3, and let's do 30 points in that vector that goes from 1 to 3. And then we'll have x2 sub 1, and I'm going to say x2 sub 2. And this is just for each one of our equations for x2. So one of these is just this, so why don't we just copy and paste it. Okay. But if I want to keep using this notation here, which maybe I do, I'll make that x sub 1 like that. Okay. There we go. And then we'll take this one over here as well. And since we're going to be plugging a vector into this, I want to make sure that I vectorize some of these operations. I want to vectorize that squaring and this division, and that should be good. Okay. And so now we can finally plot. Okay. So I'm going to want to do plot, and then x1, x2, 1, and why don't we make this one red, and we'll hold on and we'll plot another one. how about for this one, we do x1 comma x2, 2. And we'll make this one blue. And the only other thing I want to add to this is, let's maybe add in the labels. Okay, so x label is going to be x1, and our y label is going to be x2. All right, let's see if we can find our error here. So this should be with an underscore here for the 1, and for everything else I think it looks good. Let's try again. Oh, I have another one up here in this plot. There we go. Okay, so I see one of the curves here, and this is because we have one more thing to vectorize here. Let's go ahead and put a dot right here in line 16, and if we run this, we see both curves, and it looks like the solution is 2, 3. Okay. Looks like that's about where the intersection is. So let's keep that in mind, and now is what we'll do is we'll try and write a for loop to help us figure out, or a while loop, and successive iteration to help us estimate that solution. Okay. So let's maybe let's comment out all this stuff here. Okay. And I'm going to actually move this down. There we go. And so now when we're thinking about successive substitution, or Gauss-Seidel method, okay, is what we'd like to do is solve equation 1 for one of the variables and then equation 2 for the other variable. And if there was a third equation, then we'd solve the third equation for the third variable, okay, and so on. Okay. And let's go ahead and we'll solve the first one for, how about x2? That looks like the easiest approach there. So we have x sub 2 is equal to, what we're going to have 10 minus x sub 1 squared, and then this should all be divided by x sub 1, and then the second equation, let's solve it for x sub 1. Okay, so there we go, we have x sub 1 is equal to, and here we should have 57 minus x sub 2, and then we'd want to take this and we would want to divide it by 3 times x sub 2 squared. There we go. And then if we were going to start trying to set up our successive substitution, so what we'd really like is we'd like to just keep using these equations over and over. So let's just maybe generate a while loop. Okay. And maybe above it, we'll pick something for x1 and x2. How about x1 is equal to 1, yeah, let's do 1.5. And we'll do x sub 2 is equal to 3.5. There we go. So there's our initial guesses. And now, in order to make this a little bit more compact, I'm going to have us kind of convert this to vector notation. So I'm going to call this x of 1. I'll call this x of 2. And I'm going to do this down here as well. I'm going to make this x of 2. This can be x of 1 and x of 1. And then again another x of 1. X of 2 and one more here. There we go. All right, now we need to have maybe the relative error in here somewhere. Okay. So is what we'd like to do is we'd like to compute that absolute error. And that should look like the absolute value of x minus x old, right? And then all that should be divided by x. Okay. So we're going to need an x old in here somewhere. So let's just say that x old is equal to x. So every time we restart this while loop, we assign x old to be the new x that we just got. All right, and we'd like to multiply this by 100. Okay. And there might be times where maybe we don't want to compute this. How about if x of 1 is equal to 0? Okay. And actually, I want to reword this. How about if x1 is not equal to 0 and x of 2 is not equal to 0. Okay, so if both of those are not 0, we'll go in here and we'll go ahead and we'll compute the relative error. But keep in mind, x is a vector here, so I need to vectorize this. I need the dot here. Okay. All right, let's see what else. Let's go ahead and end that. Okay. And let's maybe think about some other potential things that could pop up that might be problematic. Okay. So another problematic issue would be if, in this case, if x of 1 or x of 2 is 0, that's going to be a problem with the way that we solved for our equation. So if x of 1 is equal to 0 or x of 2 is equal to 0. Let's display an error because we're not going to be able to make these calculations. Yeah, I'm going to say that. Initial guess is resulting in division by 0. And then the last thing that we need there is we would have wanted an end, but since this is taking up so much space, I'm going to break this into a couple lines. There we go. All right, and the last thing we need to build in here is something to break this. So if the max of EA is less than, let's say, less than or equal to 0.001, then we'll break. But let's also build in, and you'll see why we need this here in a minute. Let's do this for our number of iterations here as well. If the number of iterations, how about exceeds or is equal to 10, okay, we will break. And then we can finally end our while loop. And let's go in and maybe suppress some of this stuff. Let's see if we didn't suppress anything. We don't. Actually, for the sake of what we're going to do right now, let's leave x old equals x unsuppressed But when we do our next example, I'm going to go through and suppress it. Okay. We don't need to see our relative error each time. Okay, and we should build in the iterations. So iter equals 0, and iter is equal to iter plus 1. All right, let's go ahead and run it. And so what you can see is you can see all the generated x's. Let me scroll up to the top here. So on iteration 1, we just started off with that initial guess, 1.5, 3.5. And then on iteration 2, we get this. So it looks like we're getting further from the actual solution and further. And now it's starting to write things in scientific notation because we're getting so far from the answer. And you can see by the time we get to the last iteration, the 10th iteration, we have 1.7774 times 10 to the 11th. So this is diverging. This is not converging on converging on the solution. Okay. So just like when we were doing the Gauss-Seidel method with linear systems, sometimes it's helpful to rewrite these equations here. Okay. And so that's what we're going to do. Okay. We're going to resolve, okay, but we're going to solve for these in a slightly different manner. All right, so in the first equation we actually solved for x2 because that was easier, but let's actually try and solve for x1 in the first equation, and the second one we'll solve for x2. So x of 1, if we're going to solve for that, let's solve for specifically this x of 1 here. Okay, so if we're going to do that, it's going to leave us with x of 1 is equal to the square root of, and the question is what? That'd be 10 minus, okay, 10 minus x of 1 times x of 2. And let's go ahead and solve the second equation for x of 2. Okay, if we were to do that, notice that we have a couple different x2's that we could solve for, but once again, let's solve for the one that's being squared here. So we should have another square root, okay, and this should be of 57 minus x of 2. Okay. So we have our 57 minus x of 2 in the numerator there. So we want to just divide by now. 3 times x of 1. Okay. Let's, and we still have our initial guesses the same. Let's go ahead and run this here, and then maybe we'll bump up the number of iterations if it seems to be running. All right, we're actually converging on the answer 2, 3 here already pretty fast. Okay, so maybe I'll put in here format long, just so we can get a better peek. Yeah, pretty close to 2, 3 like we expected based on looking at the graph. Okay. And again, all we did is we solved for our equations here in a different manner. We solved the first one for x1 instead of x2, and the second one for x2 instead of x1, and we're getting convergence. Okay. But let's see if we bump up our number of iterations here, if we get closer to 2, 3. All right, looking pretty close, and of course you could put the relative error down a little bit. Looks like we're getting closer. So good.